Hello, my honors statistics students. This is Ms. McClellan, and this is a presentation of section 7.1, what is a sampling distribution? So here are some objectives for this section. If you want, you can pause this video right here and read through them, but we're going to talk through them a little bit at a time. So we've been talking all year about populations and being interested in data about populations. And so what we do is we take samples of the population and we collect data from that sample. Now, why do we do that? Because it's often inconvenient or difficult, if not impossible, to take the data from the entire population. We then use that sample to make an inference, which is really a decision or some kind of expectation or number about that population. But here's the thing. We can take sample after sample. Each sample is going to give us a different statistic. Okay? So recall a parameter is something that describes something about a population. So for example, what proportion of students in the United States are smokers? Okay? A statistic describes something about a sample. So in order to answer the question about the population, we take a random sample of teenagers and we ask them, or we find out the information about them, and then we use that information to make a decision about our population. So let me move this down so you can see what's underneath. Where do we put these? Here's all of our symbols and we're going to decide where they put them, with the sample or the population. So typically with populations, we use Greek letters. So mu is the mean. That's the population mean. And p, we don't use pi for p because pi is a number and it gets confusing. So here we use p. But we do use sigma, the Greek letter lowercase s. Those all describe population parameters. X bar is our sample mean. P hat, no, sorry, the hat's a little askew there, is our sample proportion. And Sx is our sample standard deviation. So X bar and mu kind of go together. That's for the population, that's for the sample. Okay? All right, just, you're not taking the AP test, but confusing these ideas is a source of confusion for a lot of students, so just be aware of that. All right, so the general idea is if we took many random samples, we would get many different values of our statistic, our sample statistic. This is called sampling variability. The value of a statistic varies from sample to sample. So if we took many samples, we would get different statistics. Note that the variable of interest can be any statistic related to our sample. So it doesn't have to be a mean or a proportion. It can be a standard deviation. It can be a median. It could be a range. It could be anything. All right, now a sampling distribution is something very specific, and what it means is if we take a population and then we took every possible sample of size n and we find the value of the statistic for each sample and we put it into a chart or a diagram or a graph, we create something called a sampling distribution. Okay, now in reality, this is often very challenging or impossible to do, because if we could do that, we could then find the value for the population. But in theory, the sampling distribution is the distribution of every possible sample of size n. So here's a little bit more in words. Let me make this just a tiny bit smaller so it fits in the screen here. Well, that's my dog snoring in the background. Hold on. Sorry. There we go. If we could take one of every possible different size sample of size n from a population, we then calculated the sample proportion for each sample and graphed all these values, we would have a sampling distribution. Because this process is not easy to do or even realistic, we use simulation oftentimes to imitate the process of taking many, many samples. So, population distribution versus sampling distribution. Suppose we have a bag full of chips. We have 200 chips in the bag and 100 of them are blue and 100 of them are red. So this is the population. We actually know what the population is in this case. So suppose we know this. Okay, so the distribution of the sample data. So here we take a sample right here at the top of size 20, and we find that we have 12 blue and 8 red, which gives us a sample proportion of 0.4, 8 over 20. Then we take another sample, and this time we have 9 blue and 11 red, so the proportion of reds is 11 out of 20, or 0.55. And yet another sample, this time we only have 7 blue and 13 red, so this one is 0.65. If we do this over and over and over and over and over again, okay, the true population proportion, P, is 0.5. We would get a distribution that looks like this. So you can see it's roughly normal, okay? The sampling, the mean of the distribution, the middle of the distribution, is equal to 0.5, which happens to be the population proportion. That's not by accident, okay? And then you can see as we get away from 0.5, we do have some samples, but there are fewer and fewer the further we get away from the true proportion of 0.5. This is a little bit repetitious. So we have a population, take samples, calculate the statistic for each one, make a chart to represent the distribution of the sample statistic. Okay, so now the other part of the chapter talks about biased versus unbiased estimators of the population parameter. And what we say is a statistic is an unbiased estimator of a parameter if the mean of the sampling distribution equals the true value of the parameter. So in other words, we may not get the sample proportion to be exactly equal on each sample. It won't be exactly equal. Maybe sometimes it will, but other times it won't. But the mean of the distribution will equal the population parameter. If it doesn't, then we say the statistic is biased. What we're doing to try to estimate the population proportion is not doing the job. It's biased in some way. Okay, so important rule. The spread of the sampling distribution, variability of a statistic decreases as the sample size increases. So as we take bigger and bigger samples, we start to see less variability in those samples. Think about it this way. If there's 30 people in a room, okay, and I want to estimate the height of those people, maybe I have one person that's 4'10" and another person on the tall side that's 6'3", right? If I'm just looking at them one at a time, I can get those extreme values. But if I'm doing samples of 3 and averaging them, then I will never get my 4'10" person as an average, assuming they're the only one over there, nor will I get 6'3" as an average, because I will always be averaging them with other people from the sample, from the population. Okay, so the variability starts decreasing as my sample size increases. As long as the population is at least 10 times larger than the sample, the variability of the statistic does not depend on the size of the population. And here this has to do with sampling without replacement. So as long as I'm not taking more than 10% of my population as my sample, then my variability will not depend on the size of the population. Once I start taking more than 10%, I start skewing things, and so that's not good. Here's a picture example of what we're talking about in terms of sample size. So here we have a distribution where the mean of the sample is 0.37. The mean of the population is 0.37. We take 1,000 samples of size 100 each, okay? And we plot them, and you can see how spread out they are. If I increase my sample size to 1,000, okay, and I'm still taking 1,000 samples of 1,000, you can see this is much less spread out. There's much less variability. Bias, variability, and shape. Think of taking shots at a target. When many shots, each sample represents a shot. When many shots are taken, when bias is present, the samples will miss the bullseye, no matter what size the sample is. When variability is present, the shots are more scattered. So what does that look like? So here we have, in the first case, high bias but low variability. So maybe we're taking very large samples, but what we're using to measure is not accurate, so we're consistently off target. So that's not good. Low bias, high variability says we are on target, but we have high variability, so our results are spread out around our bullseye. but the bullseye's in the middle. High bias, high variability is the worst of all cases. This is where you're consistently missing the target and you have a lot of spread in your data. The ideal here is no bias and low variability, where you're consistently hitting or very close to hitting your actual target. And that concludes this section. So this section is not that intense. So now what you should do is take a look at the assignment that is on Sapling for 7.1. Thank you.